All right, welcome students, and this time around we're going to talk about periodic trends, as you can see up here. So we're continuing with our conversation of the periodic table, and we kind of introduced some of the basics of the periodic table, some of the men who are involved in organizing it and bringing it together. We talked about the periodic law, which will be important for you to know for the test. Also, we talked about different things you can find on the periodic table, including how it's organized by electron configuration, by the different sublevels and energy levels. And out of that organization, we get what are called periodic trends. That's one of the cool key things about the periodic table is it is a testament to God's unique creation. And you see the organization and order of the universe demonstrated by how the elements are organized and put together, and there's a tremendous sequence to them, and it's not random, it's not by chance or anything like that. So let's continue here, just dealing with some basics on periodic trends. There are 4 of them that you're going to know, and before we get started, I'm going to tell you what you're going to need to know for purposes of the test. First thing you're going to need to know is the trend itself, and if we define what that trend is, you'll need to know kind of the definition of the trend. Secondly, you'll need to know what we call the overall trend or the general trend on the periodic table, and those should already be listed in your notes, but we'll go over them again. I will ask you that, and make sure that there is a direction to each one of those, and you will need to get the direction on the periodic table correct. And then the last thing we'll do is for each trend is we'll kind of break it down. Most of the trends will go kind of, okay, what's going on left to right on the periodic table and top to bottom, what's happening. And you will need to kind of explain the why. Why is this happening? Why is this trend doing this as I move from left to right? So make sure that you kind of, and that'll be connecting a lot of what we did last chapter, and we learned about the atom and the different parts of the atom, protons, neutrons, electrons, and how they interact with one another and where they are, what's in the nucleus, what's on the outside, and energy levels, and all those different kinds of things will be connecting to what we know on the periodic table. So let's get going. Our first thing here we're going to deal with is atomic radius, and hopefully you're familiar with that term radius. You think of a circle. Here we're dealing with or the conception is more or less a sphere. So what would the definition in essence be? I'm really not worried about what it was measured or using by, that's kind of irrelevant. What an atomic radius is, the definition is it is the going from the nucleus of the atom, from the center of the atom nucleus, to your outermost electron, which would be your valence electron. So that's kind of what we're measuring there in essence. Is your atomic radius. And you'll notice here that in general, radii decrease in size going from left to right across the period, and they increase in size going down a group or column. So if you're going top to bottom on the periodic table, radii increase. In other words, the atoms get bigger. As you go from left to right, the atoms get smaller in general. Now, if we put those two kind of trends together, we get an overall trend, and basically that overall trend is top right of the periodic table. So up there, if you're looking at helium, fluorine, that area on the periodic table, chlorine, kind of that area, those are your smallest atoms. And then moving down all the way towards, francium and cesium and those kind of down in that area at the bottom left of the periodic table, those would be your largest atoms. So that would be the general trend. So that's one of the things you need to know. And again, make sure you get that direction correct. Top right to bottom left, atomic radii increases. We're going to spend a little bit of time just kind of looking at the periodic table here. And so as we go on, what I want you to look at is just kind of this whole thing. And as we continue here, what I want to do is point out, and we'll look at different elements, but generally speaking, let's take a look at the third row then. Okay, so starting at sodium and looking as you go towards chlorine, argon, that direction. We're going to break this down. Well, why do atoms increase generally as you go from top right to bottom left What's going on? What's happening? Well, as you go from left to right, we already said that the size is decreasing. Okay, well, why? Why is it decreasing? Well, as you go from left to right, within an energy level there. So let's say row 3, energy level 3. What's changing? Well, you have sodium, and you're heading towards chlorine. Well, what's the difference between sodium and chlorine, or sodium and argon? Okay. Well, that's right. Okay, I'm adding protons. There's a difference in the number of protons. And as I add protons, what else do I add? That's right, electrons. Okay, now probably neutrons, well, not probably, neutrons are changing, but neutrons are irrelevant for our discussion here for the moment. Mainly what we're focusing in on as we go left to right, we're adding protons and we're adding electrons. Well, now how does this change the size of the atom? Because remember, if I'm adding more protons and electrons, you would expect that the atom would get bigger, not smaller. So you look at chlorine, which has 17 protons and electrons, whereas sodium only has 11. Well, wait a minute. If chlorine has more, it should be bigger, right? Except we're forgetting one very important thing. What do protons and electrons do to one another? That's right, they attract, because electrons are negative and protons are positive. And so the more of them that I have within a given energy level, the stronger the attraction is going to be. And now we have a special fancy name for that attraction, and you're going to need to know this name. It's what we call electrostatic attraction, which is the attraction between oppositely charged particles. So, electrostatic attraction, and it's spelled just like it sounds, electro and then static all together there. Electrostatic attraction is increasing. Why? As I move left to right, what am I doing? I'm increasing my number of protons and electrons. And by the way, just to pause here, all of this you should be writing down in that space that I gave you in your notes underneath atomic radii. Don't just listen to all this. You should be explaining and writing down the why. Why does it decrease in size as I go from left to right on the periodic table? Okay, well, I'm adding electrons and protons, and as I add electrons and protons, the electrostatic attraction increases. Okay, the attraction between those electrons and protons. So what does that do? Well, as that electrostatic attraction increases, it pulls the electrons in a little bit closer to the nucleus. And as it pulls the electrons in closer to the nucleus, now my distance between my nucleus and my outermost electrons is smaller or shorter. So my radius has decreased, or the size of the atom, in a sense, has decreased. Okay, so that's why over on the right side, those atoms over there generally are smaller than the ones on the left side because of that increase in electrostatic attraction. Now, what about top to bottom? Top to bottom, we said, if you look at hydrogen and you're going down to francium, hydrogen is much smaller than francium is. Well, wait a minute. We just got done saying that as you add electrons and protons, it should be smaller, right? Well, francium has 87 electrons and protons, whereas hydrogen or lithium, have much fewer. So wait a minute, based off of what we just said, shouldn't francium be smaller because it has more electrons and more protons? But it's not. So what's changing? What's different going from top to bottom that was not true as I went from left to right? Well, that's right. The energy levels are changing. You notice I'm adding energy levels, or shells, as I go from hydrogen, I only have one shell or one energy level. Whereas if I'm at francium or radium or something like that, I have 7. And so each time you add a shell, it gets a little bit further from the nucleus. Okay, each energy level is a little bit further out. So the distance is increasing there. In addition to that, we've got something else coming into play. Because I'm adding energy levels, now my outermost electrons, remember that's the one we're measuring, the distance from those to the nucleus, now the attractive force is actually weaker. Well, why is it weaker? Quite simply because in between between energy level 7 and the nucleus, what are there? A whole bunch of electrons. And those other electrons are shielding it. Remember, electrons repel each other, so they're shielding it from the nucleus. And so my electrostatic attraction is actually weaker on energy level 7 or 6 than it is there on 2 or 3 because it's further from the nucleus. So as a result, my atom is bigger and larger. So that's one of my trends. Another one of my trends is what we call, oh, real quickly before we go on to that other trend, I almost forgot. We also have what's called ionic radius, and we're not going to dive too deeply into this, but just kind of some common sense things. In general, we have ionic radius, and kind of something special comes into play because you're losing or gaining an electron. So cations, which are positive ions, are generally smaller. Why? Because they've lost electrons. Okay, so generally, they would be smaller than their parent atoms. Anions, where you're gaining electrons, are usually larger. Now, again, we're not going to go into detail on ionic radii. We mainly want you to understand the concept behind atomic radius in general. So that's about as far as we're going to delve for the moment. Now, what about our second trend? Ionization energy. Well, what is ionization energy? Basically, what you're trying to do, when we're talking about first ionization energy, is you're trying to remove an electron from an atom. And it's the energy required to do that. Because in order to remove an electron, I have to add energy to the atom for it to leave. And so that's what we mean that first ionization energy is that first electron that we're going to remove from the atom. So we're forming a positive ion here. And generally, it increases from left to right within a period. In other words, those on the right-hand side require more energy to remove an electron. And it decreases from top to bottom. In other words, those at the bottom, it does not require a lot of energy to remove an electron. So the overall trend, if I was to put those together, would be starting the bottom left of the chart, bottom left, so things like francium and whatever, and moving diagonally to the top right, ionization energy increases, okay, is what we're going to say. So those things like fluorine, helium, argon, all of those neon, those up there have a high ionization energy. In other words, it takes a tremendous amount of energy to remove an electron from them. So as we look at our chart again, what does that mean for us here as we break it down left to right? Well, again, a lot of the same reasons. Left to right, let's go ahead and look at row 3 there, sodium to chlorine, sodium to argon. Why would the ionization energy be larger? Why would it take more energy for something like chlorine or argon to remove an electron from there than from like sodium or magnesium, where it takes a small amount of energy to remove an electron? Well, quite simply, it goes back to what we were just discussing. As you go from left to right, what are you doing? You're adding electrons and protons. And so what's happening? The electrostatic attraction is greater on your right side of the periodic table. And because it's greater, it's holding on to those electrons tighter. It's more difficult to push one out as a result. So that's basically the reason. Why does it require more energy on the right side of the chart? Because it's the attraction between the electron and the nucleus, the protons, is much stronger on the right-hand side, and as a result, it requires a lot more energy to push it out. What about top to bottom? Top to bottom, what's going on? Well, again, same kind of thing. You're adding energy levels, and each energy level you add, you're getting further from the nucleus. Now, again, we're not dealing with size here, so don't mix the two up. We're not dealing with atomic radius. But what we are dealing with is, because I am further removed, my electrostatic attraction is weaker because I am farther from the nucleus. And because my electrostatic attraction is weaker, then as a result, it's a lot easier to remove an electron from something on the bottom, like francium or radium or cesium there, than it is from something at the top, like lithium or hydrogen, where your electrons are close to the nucleus. And the electrostatic attraction is much stronger as a result. So when you put those two trends together, then you get that overall trend. Make sure, again, a reminder that you are able to explain the whys, and if you need to re-watch this and listen, please do so, or if you need to back it up a little bit, please do so, because it is going to be very important to understand the whys. I will ask you some of that on the test. All right, we are done.